Okay, so let's go over the homework for the resonance and standing waves. As always, ask questions if there's something I do that you don't quite understand. So I'll try to make this quick within the 15 minutes. First question talks a review about phase difference. Okay, and we go from a phase difference of lambda to 5/4 lambda. And how does the constructive interference change? So a lot of kids get confused by this. It's fairly straightforward. Remember, you get maximum constructive interference, what I call CI, when your path difference, okay, I usually designate that as a delta lambda, but you can just call it path difference, is equal to an integer number of wavelengths. So this is goes back a bit. So it's m lambdas. Okay, that could be 0, 1, 2, 3, 4, 5. So we're starting with one wavelength path difference, so we have maximum constructive. So anything different than that is going to be less than maximum. 5/4 is somewhere less than that. Well, let's look at the other contrast, because you could be asked this. Destructive interference, maximum, and again, these are both max, occurs when our path difference is an odd half wavelength, and mathematically that's basically m plus a half. There's other ways you can do that wavelength path difference. So that's a half, 1.5, 2.5. So 5/4, 1.25 is halfway between maximum constructive and maximum destructive. So it's glass half empty, glass half full. But in this context, the amount of constructive interference decreases because we're already at max. Now, I did this in terms of wavelengths. I could just as well have done this in terms of angle or parts of a cycle in terms of pi/2, pi/4. So you have to be able to look at it like that, or even degrees, like 90 degrees is a quarter of a cycle, 180 degrees is half a cycle. So there's different ways you can quantify that path difference. All right, resonance review. I would have talked about this in class, marching band, or it could be a military. So when they march, right, a sign of a good marching band is they march in cadence. In other words, they march with a specific driving frequency, F drive. Okay, whatever that may be. Now, when they come to a bridge, especially a longish bridge which sways, well, that has a natural frequency or a number of natural frequencies. So what you don't want to happen, I've heard stories back in the 19th century happen, if this frequency matches that or one of these, then you can get a large amplification, get a resonance in the bridge, maybe not a Tacoma-Narrows type of resonance, but enough vibration above the normal that it can cause damage. So I've heard that marching bands generally break up their cadence when they are going over a bridge of some sort. Okay, standing wave fixed string, right? We have nodes, 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 nodes. So that's destructive interference, so there are 4 antinodes. Now this is, sometimes kids make a mistake. They'll say there's 1, 2, 3, 4, 5, 6. There are not. There's 1, 2, 3 at any given cycle. That's at one point, those 3 that I've drawn. And if I were to draw at some other time, then the wave would look like here, here, here. The point being there are only 3 antinodes, not 6. Which harmonic is this? Okay, well, the easiest way to do this, and there's a number of ways of doing this, is this 1/2 a wavelength is the fundamental. That's the first harmonic. So how many of those do we have? We have 1, 2, 3. So this is the third harmonic. Okay, I mean, if you look, if I were to ask you to draw the third harmonic, you might look at it like this. Here is the fundamental. It looks something like that. And then the second harmonic, what changes I have, well, if I have 2 nodes in a fundamental, I'd need to add a third node for a second harmonic. And if I wanted the third harmonic, I need 4 nodes, so I'd have to have them equally spaced. 1, 2, 3, 4, and then I would draw it in. And that matches this. So that's another way you could try to approach that. All right, what is the distance between successive antinodes? In other words, how far apart are these? And this is true for any situations. This is actually really, really important. It's always a half a wavelength. And it's also true for distance between successive nodes. They're always a half a wavelength apart. If I ask you how far apart is an antinode and a node, they're always going to be a quarter of a wavelength away. So in this case, I asked for a half a wavelength. In terms of actual length, well, then that would be roughly 0.27 meters. But we have to establish what the wavelength first is, and that's what D is about. Okay, so let me scroll a little bit. All right, so what is the wavelength of the standing wave? And this is really getting to the analysis we want to be really comfortable with. Okay, so let me maybe get rid of some of this here. Basically, ask yourself how many wavelengths are fitting into that length of 0.8 meters. So half, one, one and a half. So I'd say 3/2 of a wave, 3/2 of a wavelength, all right, 1.5 waves, sorry, equals the length of that string, which happens to be 0.8 meters. So once you set up that, that's the hard part really, is just to be able to talk yourself through that. Now you can just do the algebra, solve for the wavelength. Wavelength is 0.8 times 2/3, which is 0.53 meters. Now, this could be a guitar string that's about 80 centimeters long. So if you're playing the third harmonic on that, right, what particular sound you're hearing, that corresponds to a frequency. So that's what this analysis is going to do, is knowing the wavelength and the velocity. The velocity depends on the tension, not that you have to worry about it here, but you're told that the speed through the string is that, then we can simply do the frequency using the wave equation, right? That's just V over lambda. You can plug in the numbers and you get 187 hertz. So again, that's the third harmonic. So that is one of the sounds you might hear when you pluck that particular string. But the one that you're going to hear most dominant is the fundamental. So it's fair to ask, what is the frequency of the fundamental? Well, we don't have to go through all this analysis again. You could say, all right, a fundamental would be half a wavelength, do this analysis, figure out the wavelength, and then use this equation to find a frequency. Or you can understand that the frequency of the fundamental, which I'll call F1, right, is always going to be 1/3 the frequency of the third fundamental. By definition, it would be half the frequency of the second harmonic, etc. So 1/3 of 187 is 62.3 hertz. And the second harmonic, I could try to do it in terms of a fraction of this. It's easier just to say the second harmonic is double the first harmonic, and so we get 125 hertz. It's not the only way you can do it. You could try to do it as, I believe, 2/3. All right, let's move on. All right, now we're getting into open and closed pipes, which was the last tutorial. Let's see if I can scroll better than this. Okay, so we have an organ pipe. We want to draw the fundamental frequency. Now, you can certainly go to your notes and look at this, but and I don't want you to memorize it, but you can derive what this is just knowing two rules. The two rules are this: where the nodes form and where the antinodes form. So for any pipe, open on one end, closed on both ends, or open on both ends, is you must always get a node at the closed end, and you must always get antinodes at the open end. So these two dots represent the maximum, if you will, pressure from an air column, okay? Or if you could see the molecules, they would bunch up here and then here, okay? And then here they would barely vibrate. So to connect the node to an antinode, whoops, that's really poorly drawn. I could do better than that. Something like that, and then a half a cycle later, something like that. So it's almost like a sideways champagne glass. So why do we want you to draw that? Because it helps you visualize how many wavelengths there are. Okay, so we can see that within this length, L, I'm sorry, I guess I'm getting ahead of myself here. All it asks to do is draw that. Okay, so what frequencies will it occur? Oh, I'm sorry, it does ask for a fundamental frequency, my bad. Okay, so in order to find a fundamental frequency, we want to find a wavelength, relate that to the speed, and then go from there. So we can see from this that since we're going from antinode to node, that's always a quarter of a wavelength. So we have a quarter of a wavelength fitting within that length. So the length is simply the wavelength is simply 4 times the length. So if I want to find a frequency of that fundamental, the first frequency, that would be V 330 over 4 times the length. So we plug in the numbers and you get 110 hertz. Then it asks what are the next two harmonics. So you got to be careful here. If you remember from the notes, for closed pipes, there's only odd harmonics. In other words, the next harmonic is the third, and then the next one after that is the fifth. So that tells us that the next frequency is going to be 3 times the fundamental, 330, and this would be 550 hertz. Okay, you could go the long route and draw the harmonics for each of these by adding an extra node, an antinode, and then working out the wavelengths, but this is the shortcut to that. All right, what would happen to the frequency, the fundamental, the temperature, air went up? All right, musicians know, I think they know this, that air temperature determines how tuned their instrument is, especially a woodwind instrument or a brass instrument where the vibrations are occurring in air. Now, we never talked about this explicitly, so I can understand if you're a little confused, but higher temperature, okay, so that changes the medium, so that's going to change the speed. So higher T leads to higher V. Okay, so the speed of sound in air is fastest when air is warm. So if the V goes up, right, so again, we have F, the frequency at which we want to play a tuned note is V over lambda. Lambda is not going to change. Lambda is depending on the length of the air column, which is determined by which valves you open or close, or openings you open or close with a flute or something like that. So lambda is not going to change by air temperature, but V will. So if V goes up, then the fundamental frequency will go up. It's similar to a guitar. In a guitar, if you increase the tension, you change the speed but without changing the wavelength. So if the speed goes up and the wavelength stays the same, then the frequency goes up. So that's how you tune a stringed instrument, by changing the tension. It's hard to tune I'm not sure how you tune a brass instrument because you can't really affect temperature. Okay, now let's go to an open pipe. All right, sketch a diagram of the harmonic and determine the frequency. And we have the second harmonic. Okay, so how do we do that without just looking at a note sheet and not having to think about it? Well, we know that the open ends must always be antinodes. So the simplest one we can get, which would be the fundamental, would be antinode, node, antinode. That's the first harmonic. We want the second one. So how do we go to the second one? Well, we just add another node and then make sure we alternate between nodes and antinodes. So I want to equally space my nodes apart. So I'm going to take this one and split it in two, if you will. Okay. Ignore this one now. All right, and then between any two successive antinodes or nodes, I need antinodes, so I need to have one here and here. Okay, so I got antinode, node, antinode, node, antinode. So I connect, and I do the other one, not very well, and hopefully I can see, and that is start at a crest, go to a trough. I see that's a full wavelength. So I can say that there's one wavelength within the length of that tube. Okay, and therefore the frequency that occurs is nothing more than the length, the velocity divided by that wavelength, which is L. So put in the numbers and you get 132 hertz. Okay, so again, if you're given a standing wave, the shape, you just need to relate the number of waves to the length and then do the analysis. If you're told to draw one, you want to be able to do it based on the rules for the boundaries. So again, open ends are antinodes, closed ends are nodes, and if we go back to fixed strings, the fixed part are always nodes, and you can build things from there. Okay, nice little derivation. Velocity in a string is dependent on the tension and something called mass per unit length, which is kind of an indication of the inertia in a string. Square root of that. Okay, so I want to know if we're going to tune a piano, right, to a particular frequency, the middle C on a chromatic scale, what would have to be the tension. Okay, so we see we have a velocity part here. So there's two equations we have for velocity. There's the wave equation, which says V equals lambda F. And then there's another velocity equation that we haven't done with. It's not part of the curriculum, but I just introduced it here because it's a nice derivation. It says if you want to change the velocity in a string, you either change the tension or you change the mass of the string, or actually the linear density, the mass per unit length. So that's this equation. So basically all we're doing is combining these two. And we can say lambda F equals radical T over mu. Mu is not coefficient of friction, but it's linear density. And if you solve for, what are we solving for? Tension, right? I'd square both sides, move the mu over. I'd get lambda squared, F squared, right? All times mu. Okay. Yeah, I just want to make sure I do that right. And so if I want it at a particular frequency, then I just substitute in the 261.6 for F and leave it at that. Okay, pretty sure I did the algebra right, but I'm sure you'll let me know if I did. Okay, I'm going to stop here because I'm out of time. I'll pick up the others in another tutorial.